Hello, everyone. Today's topic is conditional probability. This is one of the concepts that I think many students feel troubled with. It seems very abstract to them, but in reality, it's not. We use this kind of a concept in our daily life. For example, if I wanted to drive through downtown Boston, and then I ask you, what is the probability that I'm gonna get stuck in a O'Neill tunnel? You might want to ask, hey, what time what are you thinking about? I say, oh, it's midnight. Then you say, oh no, it's very unlikely that you get stuck there. But if I say, oh, it's rush hour, you say, no, that the probability is really high. Almost surely that you're gonna get stuck there during rush hour. So what you're saying is actually the conditional probability. Conditioning on the time, the probability that I'm gonna get stuck in the O'Neill tunnel is different probably. Okay, so that's a conditional probability. Another example, say you want to buy a car insurance. So you call an insurance company, and then usually they wouldn't tell you, oh, hey, you buy insurance? Okay, $600 per year. They wouldn't do that. Usually they will ask you a lot of questions. How long have you been driving? Are you married? Do you smoke? Etc., etc. So what they are doing is to gather information about you, and then they put you in a category, a group of people, and use their model, maybe empirical data, to figure out the probability that you will have a car accident in the next year. That probability is also a conditional probability. All right, so that's the and then some daily life example. Here's another example which has numbers. Let's start with a class. Not that interesting, but it's okay. Very illustrative. So we have a class of 30 students in which, say, 16 have an iPhone. And maybe 14 have an iPad. I'll just randomly give these numbers. 10 of them have both. So the question is this: suppose you pick a student, and this student has an iPhone. What is the probability that this person has an iPad? This also has an iPad. Okay, so what we're looking for is a probability that someone having an iPad, given, this is called a given, we use this notation, a bar, given or known, this kind of language we use a lot, given that this person has an iPhone. So that's what we're looking for. It's a conditional probability. Let's analyze the situation. So, you know this person has an iPhone. That will restrict ourselves in this sample space. So given the new information, we have a new sample space. Instead of 30 students, we have 16 students. And out of these 16 students, 10 have both. That means they have an iPad. So reasonably, the probability would be out of 16, 10 of them. So it would be 5/10, 5/8. Now let's draw a Venn diagram. And that's about 30 students, sample space, and you have iPhone, iPad. Let's call this total samples, the whole sample space, and iPad, that's the ID. iPhone. E. Both, 10 have both. And iPhone, you have 16 here and 4 here. By the way, you always put the total 14 minus the intersection, 10 of them, to put this number here. Do not put 14 here. That's the convention and it's more convenient. And we also get some other information, say in this class, 10 have none. They have neither. Okay, so you know that somebody has an iPhone. Oh, we know that. That's the new sample space. And within this group of students, 10 have both, so 10 out of 16. All right, so that's the common sense of a conditional probability. Now, what is the definition? Definition of a conditional probability is very similar. A given B, again, B is the given information. Okay, it's a given info. We're looking for the probability of A when knowing B. Is defined to be the probability of A intersect with B divided by the probability of B, provided that the probability of B is not equal to 0. Probability of B is 0, that means B will never happen. And if it doesn't happen, but you know it happened, that's kind of a contradiction. So we require the probability of B not equal to 0. So this ratio is meaningful. This conditional probability using our common sense fits very well about the definition. When I pick a student, we can assume equally likely condition to be held. So this one, you have a 10 out of 16, right? Now let's divide the numerator and denominator by 30. So 10 out of 30, 16 out of 30. Suddenly, the numerator becomes the probability of having both, and the bottom is the probability of having only iPhone. So that's exactly what this definition is telling us. Okay, so let's have a look at a very simple example. Another simple example. Say, I tell you the probability of A equals 0.6. Probability of B equals 0.5. I just randomly pick some numbers. Okay, the probability of A. Let's make a little bit flavor, add a little bit flavor to that. The union is 0.7. And we're looking for the probability of A given B and the probability of B given A. All right, we don't have anything for the moment other than the definition. So let's go ahead using the definition to figure it out. Probability of A given B, that's the probability of the intersection over the probability of the given information, which is B here. We don't know the probability of A intersect with B. That's not given here, not given directly. But we know the probability of the union. Then we should be able to figure out the probability of the intersection. We have a union rule, or addition rule, which is the probability of union equals the sum of the probabilities minus the probability of the intersection. So plug in 0.7 here, 0.6, 0.5. We have a 0.4 for the intersection. All right, so now we plug in 0.4 here. Probability of B, 0.5. So we have a 0.8. Similarly, we can work with the probability of B given the probability of A. Again, the probability of intersection divided by the probability of the given information, which is A. And we have 0.6 here on the bottom, and the numerator is still 0.4, so you have 2/3. So in general, these two are different, okay? You cannot change the order of A and B. All right, let's have a look at another example. Okay, so it's another simple example. Using contingency table or two-way table. The numbers are just randomly picked, right? Oh, well, not randomly picked. They're nice, add to be 200 total. That's actually designed. But the scenario is really, it's arbitrary. All right, so suppose we have a group of people, 80 Republic, hey, hold on a second, no, a group of people. Totally, we have, I think, 300 people, 300. Republican, totally have 90, independent, 120. And here we have 160 and 140. So 160 people in this group voted for Trump, and 140 voted for Biden. Now we're interested in some conditional probabilities. The probability that somebody would vote for Trump, somebody in this group, knowing that this person is, say, Democrat. Okay. So you use the definition, right? Intersection, the intersection of somebody who voted for Trump and a Democrat, divided by the probability of the Democrat. This is use the definition. So intersection, that would be 20 out of 300. And Democrats, totally how many Democrats? 90. So 90 out of 300. That's exactly 2 nines, which is also the same as 20 out of 90. All right. Another one, probability somebody would be a Democrat if we know that person voted for Biden. You can use the definition, but we can just simply use these numbers here. So let's do that. Biden, totally 140 people voted for him, so 140 on the bottom. Democrat and vote for Biden, that's 70, so that's 1/2. Okay, so that's a simple example of using two-way table, or contingency table. All right, let's move on. The next example, it's probably a little bit hard. A student is taking a 1-hour limit makeup examination. Suppose that the probability that a student will finish the exam in less than X hours is X over 2. X is between 0 and 1. So the probability that the student would finish the exam in 1 hour, and that's half. That means the probability that the student didn't finish the exam during the 1 hour time would be also half. To get 1 minus that. Given that the student is still working after 0.75 hours, what is the conditional probability that the full 4 hour is used? Okay, so we're looking for the probability that the full hour is used, the student used the full hour. Uses the full hour. Given, it's a conditional probability, given that the student is still working on the exam after 0.7 hours. You can rephrase this event because he's still working after 0.7 hours. That means the student didn't finish the exam at 0.75 hours. The student needs to continue working, so it's let's put the language here. It's still working. Still working after 0.75 hours. It's a little bit cumbersome to write these words, so let's just make this A, this B. So it's the probability of A intersect with B divided by the probability of B. The probability of B still working out of 0.75. That is actually 1 minus 0.75 over 2. Okay. The reason is that this is the probability the person would finish the exam in less than 0.75 hours, but the student's still working, so he didn't finish at that time. So you do the complement. And then the numerator says that the student is still working after 0.7 hours, and also the student would use all the full hour, and the intersection of these two is simply A itself, right? Because the student is still working after 0.75. Oh, the student uses the full hour. That's implying the student works after 0.75. So A is like a smaller subset. It's a subset of B. So the intersection is simply A. That's just the probability of A, which means the student uses the full hour, which means the student didn't finish the exam within 1 hour. So it's 1 minus 1 out of 2. All right. So we have a 0.5 and 0.5 divided by the 0.375. Okay, and then 1 minus that, 6 to 5. That is about 0.125, 0.125. 0.1 divided by that, 0.8. Okay, so that's the conditional probability. So if we know that students still working after 3/4 of an hour, it's very likely that the student would not finish the exam on time. All right, so this is another example. Hold on a second, let's erase these. I wanted to talk about a little bit about two conditional probabilities and then finish the slide. Okay, so we have a standard deck of 52 cards. We have 4 suits. Each suit has 13 cards. Club, diamond, heart, and spade. And each suit has cards from 2, 3, 4 to 10, and then Jack, Queen, King, Ace. All right, totally 52 cards. And you select 2 cards one by one without replacement. If I know that the first card is a heart, what is the probability that the second card is also a heart? You know the first card is heart, you already picked one. We're not going to use the formula for that, right? We can use our common sense to figure it out. You know the first card is gone, and so you have 51 cards left for the second card to be picked. And the first card is a heart. Well, there are 12 hearts left, and the probability that the second card is a heart chosen from 51 is 12 out of 51. Okay. So I want you to have some sense that if an event involves, say, 2 steps or several steps, say 2 steps, if you know what happened in the first step and the probability of something happened in the second step, is usually easier to find. You know the situation already, so it's easier to find. However, if I wanted to find the probability of H1 given H2, so you know the second card is a heart, what is the probability that the first card is a heart? Now that kind of a probability is not that trivial, okay? And this kind of probability is called a posterior probability. And we will have a systematical way to solve that. And that's called Bayes rule or Bayes formula or Bayes theorem. Okay. That to be discussed in another small lecture. All right, so that's for today. Thank you for watching. Bye-bye.